Okay, so I like to write electron configurations with the periodic table. So let's talk about how to write electron configurations with the periodic table. So the periodic table, if you look at it, is really nicely organized for this purpose. I'm going to draw my really poor rendition of the periodic table here. Let's see, that's supposed to be the same height. And that goes there. Okay, so that's the periodic table, right? Now, I want to tell you guys something kind of interesting. If I was to draw the periodic table accurately, I would actually take a scissors and cut the whole periodic table right here and glue this part in. That make sense? Really, this part is in between here. So why don't we do that? Well, because it'd be way long and awkward, right? But that part is, as you go lower in the periodic table, things are bigger. You can fit more things in a bigger suitcase, right? If you get a bigger atom, you can fit more electrons in. Does that make sense? As you go lower in the periodic table, you can fit more electrons in, so the periodic table gets longer across. Does that make sense, everyone? Right? So if we look at the periodic table, what about the top row? How many things are there? 2. How about the next row down? There's 8 things across. How about down here in this row? 18 things across, right? The reason is because we can pack more electrons into one energy level. Got it? Okay. So let's look at it. And I'm going to name each block for us so that you can use this in electron configurations. This is called the S block. This is called the P block. This is called the D block. It's like a prison. It's like a prison for the electrons, yes. The S block, the D block, the P block, and last but not least, what do you guys think this one is down here? When we get really high energy, we have enough room finally to throw them in the F block. Helium is a lie. Helium is part of the S block. Right? Make sense? Because the top row only has 2. But why do they put it over there? Because it's a noble gas. It doesn't react with anything, so they put it over there, right? So it kind of is like a little weird at the top of the periodic table in that regard. So, there we go. Got it? Okay. So let's use this to write electron configurations. What is the top row, by the way? We have 1, 2, 3, 4, and so on and so forth, right? So let's use this and write an electron configuration. And we're going to first start with sulfur. And I'm going to show you how this works using these blocks. So, sulfur. And I'm going to do the electron configuration this way. I'm going to have increasing energy. So as we go up this way, we have increasing energy. Does that make sense? Okay? So what I'd like you guys to do, I'm going to draw it on the board, but you guys can just do it on this worksheet. And it says Aufbau diagram on top. Aufbau diagram. Do you mind handing it out? So I can keep going. So Aufbau diagram. So what do we have at the very bottom of the Aufbau diagram? Or we can look at it this way. What is the very lowest energy? What is the lowest energy place we can put the electron? right here is what? 1s, right? So in 1s, how many electrons can we put?
2.
Okay, we can put 2 electrons because each orbital can fit 2 electrons, right? Well, let's look here. On 1s, how many elements can we count over? 1, 2, right? So there are 2 elements in the row. There are 2 electrons we can fit in 1s, right? Now, if we look at that sheet, what's the next one up? 2s. And if you look right here, what's after 1s? What's the next? Row 2s, right? So what can we write there? 2s, we can put 1, 2 electrons. So let's go with sulfur one more time. Sulfur, how many protons does sulfur have? Sulfur has 16 protons. How many electrons does a balanced sulfur have? 16 electrons, right? So we're filling these in. How many do we have so far? 1, 2, 3, 4. So how many more electrons do we need to put here? 12. So where can I put the next electrons after 2s? Yes. Look at the periodic table. After we have 2s, what comes next if you just keep reading left to right? 2p, right? Second energy level, p block. 2p. P, if you look at your Aufbau diagram, is slightly higher energy, isn't it? But what else do you notice about it? It has 3 spots. Why does it have 3 spots? Because it can fit 6 electrons, right? So what do we have? 1, 2, 3. Hold on. Why did I put them like that? Remember Hund's rule. Aufbau principle is why we're starting low energy and filling to high. But Hund's rule says if we're in the same energy level, we put 1 electron first, then pair them, right? So how many more electrons do we have? 1, 2, 3, 4, 5, 6, 7. We only have 7, but we're going to 16, right? 7, 8, 9, 10. Now what? We need to go to the next level. So what's next? We're at 2p, so now we start on the next row, and where are we? 3, 1, 2, 3, S block, right? 3s, how many electrons go there? 1, 2. So how many have we used so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many more do we need to put in? 4 more electrons to go. And where are we at? 1, 2, 3, S, 3, P, right? You see we're just counting down. So we're going to have 3P. 1, 2, 3. How many electrons? So 1, 2, 3. Why did I do that? They have to be on the empty bus seat before they're going to pair up, right? And now the 4th one pairs up. This is the electron configuration for sulfur. Got it? Do you guys see how easy it is if you follow the periodic table? You don't have to use that weird, funky chart the book has, or Alex. It's way easier to just look at the periodic table and count down, in my opinion. So, what's the electron configuration of this? Here is it at an Aufbau diagram. How would I write it? Well, first I have energy level 1, S. How many electrons? 2. Then what? 2s what? Then what? 2p, 6. There's 6 electrons, right, in 2p. Then what? And then lastly what? 3p4. Everyone got that 4? Make sense? This is the electron configuration for that. Now I need to define something for us real quick. Add this to your notes. We have things called valence electrons, and we have core electrons. Valence electrons are just the name we give to the outer shell, and core is inner shells, plural, right? So valence is the outer shell. What does outer shell mean? Outer energy level. So can we find, just real quick, let's practice, can we find our valence electrons in sulfur? What is sulfur's valence electrons? Where are they? Don't count them yet, just tell me where they are. Not the p block, only. Energy level, which is N, which is found where? The number. 3, right? So how many, where are they? Those are valence, and those are valence, right? These are valence, aren't they? Can I see that? Because they are the third energy level. They're the highest energy level, right? Why is 2p not count? Lower energy level, yeah, it's 3. Why does S count even though it's lower energy than P? Because it's not S and P that we're talking about. We're talking about the shell, not the subshells. The shell, which is 3. So valence electrons here are also here. Let me show you in the electron configuration. Do you see that? Those are the valence electrons. 3s2, 3p4. Got it? Really, really, really important. The whole reason we're doing any of this is because we care a lot about valence electrons. Yeah. Why is 3s what? 3s is valence because it's in the outer shell. What is the shell? If we look at our electron configuration, like if you look at 3s2, what is 3? That's the shell, right? What is S? Subshell or shape, right? So the outer shell is which one on sulfur? It's 3. Because, by the way, how do you know that? If you want a quick trick, what row is sulfur in? The third row, right? You see that? 1, 2, 3. Sulfur's in the third row, so you already know that its valence electrons are going to be the third shell. Got it? It's all connected to the periodic table, actually. So, and by the way, what would this look like? Just FYI, what would this look like? Well, here's your nucleus, right? And you'd have 1s. What would 2s look like physically? What would it look like? If 1s is a sphere, what is 2s? A sphere, but what's different about it? Thank you. It's bigger, right? We stretched the spring out more. The electron moved out further. Okay, 2s. Now what? What do we have now? 2p. What does p look like? No. Now it's the same size as 2s, but they're dumbbells. Right? Here's x, right? px, py, and then where's pz? Coming out at us, right? The same size as the sphere. Now what? Where do the next electrons go? 3s. What does 3s look like? You guys seeing it? What does 3p look like? Dumbbells, but they're bigger, right? They fit. Now, do you guys see how this works? We're describing that and where the electrons are with electron configuration. But that is what we're representing the whole time, right? Right, there's our 3p, isn't it? Can you guys see that? Okay. So, now, because we believe in torture, let's torture ourselves with tin. Why is tin torture? Well, how many protons does tin have? 50 protons if you look at the periodic table. So how many electrons? This will be fun. Okay? Increasing energy level, right? Okay. So what do we fill in first? 1s. If you look at the Aufbau diagram you have, 1s. What's going to be next? 2s. Right? Sorry, let me do these arrows in different colors so you can see them better. That'll be better. Now what's next? After 2s, what do we have next? 2p. Which is right here. I cheated. I should have put one arrow in each one. I'm sorry. Then paired them. Forgive me. Okay, what's next? Now what's next? 3p. Whew. Man, I'm getting tired. Okay, so because I'm getting tired, I'm going to talk about something. Where are we going to end? Where are we going to end? How would I predict where I'm going to end? Well, let's do this. Where is tin? SN right here, right? What row is it on? 1, 2, 3, 4, 5. Fifth row. Which block is it in? P block. What space in the P block? Second. So what is the very last thing I'm going to have? 5p2. Right? So that's kind of nice to know. So I can know that I still need to keep going, right? Little hint for you guys of how to do that. So now 3p, 6. What's next?
4s.
4. Very good. 4s has what? 2. Now what? 3d. Why? Because it fills the highest energy first, right? 1, 2, 3, 4. It fills the highest energy first. Now, what did I say about orbitals? When you're cramming more electrons into these really tight orbitals, what happens? It's harder and harder to fill them up. So D is higher energy, right? It goes S, and then what's higher energy than S? P, right? You guys see it? It goes S, and then P is higher energy. Right? 3S, 3P is higher energy. But then what does that mean? 3D is even higher energy. And in fact, 3D is such high energy that it is higher than 4S in energy. Why do we call it 3 then? Because physically it's the same size as the other 3s. Does that make sense? So this is where I get a little tricky. What is the valence? Oh, we'll do it at the end. When we get tin, we're going to do it at the end. Don't forget it's the outer shell, the highest energy shell, not subshell. So the valence wouldn't have anything to do with the letter. It still only has to do with the number. So let's keep going, and I'll show you in a second. Okay? So now we did 3D. Now what do we do? What's the next highest energy? 4 what?
P.
4p, right? Now what? What's next?
5S.
What's after 5s? 4d, right? Here's S, P, and then D is going to be up here. All right, now what? 5p. Is that it? Like 2 electrons in that one? You guys see that? Now, what? How many electrons are there here?
48.
Should be 50. Don't mess with me. All right, there's 50 electrons here, right? Now here's my question. Where are the valence here?
5.
What are the valence? Good. These are the valence. 4d is not valence because even though it's high energy in here, it's still physically inside. It's with the other 4s. It's inside there. So that doesn't matter. Now, last thing I got to tell you guys about this to make sure we drive this point home. Why? Who cares? Why have we been doing all these electron configurations? I'm going to write something down for you. That's really important, and the reason why we do all this and why valence electrons are so cool. They're pretty cool. Every chemical and physical property comes from valence electrons. Wow. Think back for a second. Chemical and physical properties. Chemical and physical. So what am I telling you when I say that? Literally everything. What is a chemical property? What it reacts with. So I'm telling you every chemical reaction happens because of what? Valence electrons. How about physical properties? Color. Phase, like is it a solid or liquid? Everything. Strength, ductility, conductivity. Everything happens because of its valence electrons. Actually, a couple of those really small properties, a couple little details that might happen because of some core electron stuff, but basically everything, the lion's share happens because. But even that happens because of electrons. So why do we care so much about electrons? Because they make everything happen. Understand? So that's why we're doing this. So you guys go ahead and do the next one on your own. All right? And by the way, really quickly, before I move on, tin. Can we write the electron configuration of tin? I should do that for you guys real quick. We have time. So, what is it? What's the electron configuration? 1s2, 2s2, 2p6, 3s2, 3p6. Then what? 4s2, 3d10, 4p6, and then what? 5s2, 4d10, and then what? 5p what? 2. Very good. Awesome. That's fun. All right, now that is painful. That is way too painful. So what are we going to do to make our lives easier? Do you guys notice that a lot of these have the same exact, like we're writing the same thing over and over again? Because up to each noble gas, the configuration doesn't change. The valence, which is after the noble gas in the next row, that's what changes, isn't it? And all we really care about is valence electrons in most cases. So can you guys spot for me where the noble gas is here? What's the electron configuration of this? Put some brackets there. What's the electron configuration? I mean, what is this? Yeah, what's up?
Just that it's AR and then
Yeah.
-2.
Very good. So what is this thing right here? Krypton. So let's make our lives way easier and use what we call the shortcut method. I'll just use krypton to represent. Did I skip anything? Technically, no. I just represented all these electrons with the noble gas, and then I will put 5s2, 4d10, 5p2. That is the shorthand way of doing this electron configuration. Make sense? All right. So finish those up, and I actually... Go ahead.
I just have questions.
Okay, yeah. Let me point out one last thing before I finish, which is kind of interesting. How many electrons does oxygen want to gain? We're going to worry about ions in a minute here. 2 electrons, making it, which is neon. How many electrons does nitrogen want to gain? 3, making it what electron configuration? Neon. How about fluorine? How many electrons does it want to gain? 1, making it which electron configuration? Neon. What about sodium? Let's make it way more complicated, right? Sodium. What does sodium want to do with its electrons? Give away how many? 1 electron. If sodium gives away 1 electron, what electron configuration will it have? No, it's giving away 1. It's going backwards. To which noble gas? Neon. Let's do one more just for fun. How about magnesium? Magnesium wants to give away how many electrons? 2. What electron configuration will it then have? Oh, neon. Right? So they all basically want to form the noble gas electron configuration. And by the way, you'll be asked to write ions sometimes. When you're asked to write the electron configuration of an ion, if all else fails, guess the noble gas, by the way, right? But all you're going to do is add or subtract the number of electrons for the charge that it has, right? All right. So don't forget, the way we can do this really easily is just count down the periodic table, right? 1s, 2s. 1s, 2s, 2p, 3. Right? Then we get to the. So really quickly, as part of the shortcut, what do you notice about D? This is 1, 2, 3, 4s, and then what about D? 3d. So, note to self, subtract 1 for D. And the last little bonus point I have for you guys here, little hint, subtract 2 for F. Got it?